Hi everyone, Professor Bob Young here. In this instructional video, we are going to look at what's called double angle, power reducing, and half angle formulas, and we'll show you where a few of these are derived as well from our sum and difference formulas that we previously looked at. So the objectives are using these and why do you use them? Double and half angle formulas are used in calculus to make integration easier and also to find some of those angles that are not nice friendly unit circle angles. And the power reducing formulas are also used to simplify calculations necessary to solve a given expression. All right, so here are the formulas that we're going to look at, starting with the double angle formulas. So notice the three double angle formulas. The sine of 2u, which is the double angle here, is going to equal 2 times the sine u times the cosine u. All right, so for example, if I take the sine of 2u here, let me just go ahead and write that as the sine of the angle u plus u. So I'm taking this double angle and breaking it apart into u plus u. And from our previous lessons, we have learned that the sine of the sum of two angles is equal to the sine of the first one. So I'll put the sine u times the cosine of the second one plus the cosine of the first one times the sine of the second one. And as you see, that is going to equal, collecting like terms, you can put 2 sine u cosine u or 2 cosine u sine u, but that is where they derive the double angle formulas, is from the sum and difference identities, which there are many proofs of these, and you could go back and look at those if you wanted to as well. Cosine 2u, we could make a similar argument. We could break apart the cosine of 2u, the double angle, into the cosine of u plus u, and then we can use our sum formula for the cosine here, and that would give us cosine u times cosine u, since a and b are the same angle here, and then this will just be uu minus sine u sine u. So this would be one of those angles. You'd get cosine square u minus sine square u. And then you can see where these other ones could come into play based on the Pythagorean theorem. So in other words, if you took this one and you wrote what sine square u equal to, your major Pythagorean identities, that would be 1 minus cosine square. So you could have minus out here, minus this, and that would give you 2 cosine square u minus 1, or change this to 1 minus sine square, and then you can see where all of these come from the sum and difference identities. All right, so let's look at an example here. We'll start with the double angle formulas. Now it says if the sine of theta is 4/5 and theta lies in quadrant 2, find the exact value of the sine of 2 theta. Now we'll go ahead and write the formula here. All right, so I put sine of 2 theta equals 2 sine theta cosine theta. Now over here we've got the picture of the right triangle here in the second quadrant. So I went ahead and I put the sine, remember, is y over r. So we put 4 over 5 here. Now many of you will recognize the famous 3, 4, 5 right triangle, but remember x is along the negative side here. So you'll end up with -3. So we've used the Pythagorean theorem many times to get these. So let's go ahead and solve this now. So the sine of theta was given as 4/5. So all we have to do is go ahead and plug in these values. So 2 times 4/5 times the cosine would be adjacent over hypotenuse, or x over r, which would be -3/5. And it's just a matter of multiplying the fractions together here, and you will get -24/25 for the answer here. All right, in this example here, we'll use the same right triangle. In quadrant 2, it says find the value of the cosine of 2 theta. Now remember, here's the angle formulas for the double angle here. So let's go ahead and we can use any of these to get the answer. So I'm going to go ahead and rewrite the cosine of 2 theta. I'll use this first one. You can use any of the three formulas because they're all um, equal, and we'll just go ahead and rewrite u as theta. And then so cosine square, well, we know the cosine up top here was negative 3/5, so we'll take negative 3/5 and square it. The sine was 4/5, so we'll take that and square it. And once again, we'll go ahead and simplify this, so we'll end up with 9, positive 9/25 squaring that, minus 16 over 25 will give us the final answer of negative 7 over 25. All right, now using the double angle formulas and the sum and difference formulas, we're just going to throw those last few lessons together and do a monster verify the identity here. And this is another thing you can use a lot of your formulas for. Remember, one formula can be used to verify the others as we progress here, and we can just build step by step here. So we're going to verify the sine of 3 theta, 3 times an angle, is equal to 3 times the sine of the angle minus 4 times the sine cubed of the angle. And once again, like we proved earlier when we were proving the sum and difference formulas, we split the angles up in order to use things we had previously learned. So we're going to go ahead and take the sine of 3 theta and break it into 2 theta plus theta. And then first, I'm going to use my sum and difference formula for sine here. So I'm going to go ahead and plug this in. So I'm going to say this equals the sine of 2 theta times the cosine of theta. So I'm just letting alpha be 2 theta and this one beta be theta, plus the cosine of 2 theta times the sine of theta. All right. Now, if you're trying to verify something, you always have to keep in mind what you're going to try to end up with on the right side here. All right. So we're trying to get everything in terms of sines here. Now, notice on these double angle formulas here, there's no doubt what you have to put for the sine of 2u or 2 theta here. There's only one choice. So we're going to go ahead and put in for this one. Okay, because we're trying to show that this comes out to be this over here. We're going to put 2 sine theta cosine theta, and then we got to bring down this cosine theta, plus over here the cosine of 2u. Now, since I'm trying to get everything in terms of sines here, which of these three do you think I would use? Well, I think it might be advantageous to use this bottom one. So this one, I'm going to go ahead and put 1 minus 2 sine square theta, and then times the sine of theta. All right, so cleaning this up on these verification property or verification problems, we're going to say this is 2 times the sine of theta times the cosine square of theta. And then if we want to, we can go ahead and distribute this on this side. We can run the sine through here. So I'm going to say that's the sine of theta minus 2 sine cube theta. Now, y'all thought we were done with verification from earlier parts of the chapter when we did all those verification problems. And it's like, no, we're not done, no. Now, I'm starting to like things a little better. Some of you go, I hate this. I don't like it better young. But anyway, when I see the cosine square here and I'm trying to get to all sines, watch what I can do. Now, you got to know your identities again. Practice these fundamental identities, and you should know this one. The cosine square is 1 minus sine square theta. And I'm just going to go ahead and write the rest of this here. All right, so now we've got another distribution, so we can say 2 sine theta times 1 is 2 sine theta, minus 2 sine theta times sine square theta is 2 sine cube theta, and then plus sine theta minus 2 sine cube theta. Now also remember, when you multiply the sine here times the sine square, all right, you do not mess with the angle here. That's sine cube theta. Do not mess with the angle. I see students try to do that and put, theta squared and 2 theta here. No, 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 no. All right, so equals, go ahead and collect like terms. 2 sine theta plus sine theta will give us 3 sine theta. And then minus 2 sine cube theta minus 2 sine cube theta would be minus 4 sine cube theta. Fried, dyed, and verified. So you can see from previous formulas, we can build on those and just keep making life easier. And when y'all get to higher level mathematics courses, this is going to be a great thing for you to help simplify your amount of work. All right, well, we use the double angle formulas to verify identities and to solve some problems. So now we're going to go ahead and look at the power reducing formulas, which will make your life in calculus easy for integration and stuff. Those of you go into calculus. Now, if not, that's all right. We'll go ahead and show you how these work. Now, what we want to try to do, it says write an equivalent expression for the sine to the fourth power x that does not contain any powers of trigonometric functions greater than 1. So the power reducing formulas will take these higher powered trigonometric functions and reduce them down to single exponents on the cosine here. So what we're going to do is we went ahead on this one and we took the sine squared of x when we broke it into square there. So if we square this, we'll get this. And then we used this identity here, 1 minus cosine 2u over 2 is sine square. And now we're going to go ahead and keep going. So I'm going to take and put 1 minus cosine 2x over 2, not once, but twice. So we're going to go ahead and show you how to do this. Now, one thing you're going to learn in calculus is if you have a denominator of 4, sometimes it's much easier to take that denominator of 4 and write it out front. All right, so it's going to take those 2's and just make this a lot easier to deal with. Okay, now I am going to FOIL this those trigonometric binomials, so to say. That's a lot of words to spit out there. All right, so we're going to FOIL this just like we did in algebra. So 1 times 1, first 2 terms 1. The outside 2 terms is minus cosine 2x. The inside 2 terms is minus cosine 2x. And watch the signs on the last 2. Negative cosine 2x times negative cosine 2x is positive cosine square 2x. Again, do not mess with the angle when you are multiplying trig functions. You only square the cosines here. Do not touch the angles. And then we're going to go ahead and collect like terms here. And I might move this up and put, let me go ahead and bring this up. 1/4 times 1 minus 2 cosine 2x. So we got a -1 and a -1, a -2, plus cosine square 2x. Now notice the direction said we don't want powers greater than 1 in here. We still have that power of 2. So this is one of those where we're going to have to use this power reducing formula again. So what you have to see here is if you put 2x in here for u, all right, this is going to be 2 times 2x. And then what we're going to do is replace this whole thing. So the cosine square of 2x is going to equal 1 plus the cosine of 4x over 2. All right, using this formula. So all of this is going to change to this, and we're going to put it right here. That's our next move. All right, so here we go. So these get a little bit complicated. You have to just take it step by step and be careful. All right, so we're just taking this and putting in the cosine of 4x over 2 here. Now, we still have a fraction here and some things we can simplify inside the parentheses. So what I'm going to do next is I'm just going to put a 1 under each item here. and then I am going to get a common denominator of 2 on everything. Okay. Now this last fraction already has a common denominator of 2, so we're just going to leave it alone. And also notice that all of the cosine powers are now not greater than 1, they are 1, and that's what we're trying to achieve. So multiplying top and bottom of this by 2, 1 over 1 is 2 over 2 reduces to 1, minus 2 times 2 cosine 2x is 4 cosine 2x. So now we can say this is 1/4, and we can collect like terms in here. We can say that 2 plus 1 is 3. All right, so I'm trying to circle this. This 2 and this plus 1 here is 3. Minus 4 cosine 2x is here, plus the cosine of 4x all over 2. And then the final answer here, you can take this 2 and this 1/4 out here, and you can combine this. You could take, again, in calculus, this is going to be huge. So this is almost like you could factor out this 2. You could rewrite this as 1/2 out here times the top. So we're going to say this will equal 1/8 times the top. I'm kind of running out of room here. You usually do on these is run out of room. And then you may even want to distribute the 1/8 through. So if you want to, since I'm running out of room here, if you, I mean, sometimes they'll take this answer, you know, depending on the software, if you're using software programs or something, or sometimes it'll want you to distribute that through there. And if you do, you're going to get, watch your reducing here too, 1/2 cosine 2x plus 1/8 cosine 4x. So this would be 3/8. 1/8 times -4 is -1/2 plus this. So I would take either of these two answers on the test. Alrighty. Power reducing, well, practice several of those. I gave you several in the homework, so those will definitely keep you busy. All right, so we've done some power, some double angle formulas, power reducing formulas. So now we want to go ahead and use some half angle formulas here and show you how these work. So it says on the half angle formulas, you've got the sine of a half angle equals plus or minus the square root of 1 minus cosine u over 2. And the only difference in these, the cosine of the half angle, these signs change from minus to plus. And the tangent one here, I think if I was using tangent, I would use this formula because this is a little bit easier. Now the sines of the sine of u over 2 and the cosine of u over 2 depend on the quadrant in which the half angle lies. All right, now we're going to go ahead and use an example here, and then we're going to go to the homework and do some examples as well on all of these things we've been looking at, and maybe do a few more examples on those. And we're going to look at, it says here, use a half angle formula to find the exact value of the cosine of 105 degrees. All right, so we're going to go ahead and write this formula here and put the cosine of 105 degrees. Now this is the half angle. All right, so if a over 2 equals 105 degrees, multiplying both sides by 2, we're going to go ahead and say this is going to equal an angle we know. Now what sign is the cosine in the second quadrant? The 105 degrees is in the second quadrant, so that's what I mean by it depends. The signs depend. You can't put plus or minus for the answer. The cosine is going to be negative in the second quadrant. That's the x value. So we're going to go ahead and plug in 1 plus the cosine of the angle would be 210 there. So we're going to say, so this is going to be one we know and love, all over 2. Now we get to simplify this. This is going to be fun. This is going to equal minus, so those of you that love fractions, you're just in for a treat here. 1 plus the cosine of 210, if you remember on the unit circle, is negative square root of 3 over 2 over 2. So you have this, what I like to say, complex fraction, fractions over fractions. Now how I teach my students to do this, to clear the fractions here, is multiply by the LCD of both top and bottom to clear complex fractions. So I'm just going to multiply top and bottom by 2 there. So that's going to give us minus the square root of 2 minus the square root of 3 over 4. So I distributed the 2 in the top. 2 times 1 is 2. 2 times this fraction, the 2's will cancel out, leaving you with minus square root of 3 over 4. Now remember, this square root of 4 is in the denominator. It's under a radical, and the square root of 4 will simplify as negative 1/2. You could also take this division by 4 and think about it this way. You could rewrite that as 1/4 times this quantity. All right, so the square root of 1/4 comes out. Don't lose the negative sign here, as 1/2 times this, don't lose the square root either, times the square root of 2 minus the square root of 3. Now, how could you check this? If you put this in your calculator, the cosine of 105 degrees, the newer calculators will give you this. So that's great, but again, you have to show your work when it gets down to it. And plus, you guys need the algebra practice. Calculus, when you get there, is a lot of algebra in it, so you have to make sure your algebra is solid. And remember, these formulas are going to be used to help you do things in calculus and make your life easier. Differentiation, it's going to make, a lot easier to deal with certain things. Okay, and you could put this in your calculator. It might get a decimal on your calculator, right? It might give you an approximation, and if you put all of this in, it should be the exact same decimal digit per digit. All right, so you can check these. All right, so we were just dealing with the half-angle formulas here, so I wanted to get to some of the homework problems and show you what I meant by the sign here. So all they want on the first few examples, make sure you know what quadrant you're in here. Here's how the half-angle formula works. So again, if this is the half-angle, u over 2, then this is u if you double it. But the sine of 34 degrees in the first quadrant, hopefully everyone knows the y value there is positive. So I was just kind of giving y'all a feel on these half-angle formulas and how they work and so forth. All right, now the cosine of 197 is in quadrant 3, and again they took the half here and doubled it, but you should know just the sign in quadrant 3, the x value cosine would be negative there. All right, tangent of 148 would be in quadrant 2. Again, here's the half, you double it. Remember, in quadrant 2, x is negative, y is positive. Sine over cosine, tangent will be negative in that quadrant, and so on. Now, I've given you an example like this one earlier in the video, so you can go back and write sine of the double angle 2 theta would equal 2 sine theta cosine theta, and then go ahead and use your right triangle trig and get the number and solve there. And the tangent of 2 theta here, I don't know if we've done a tangent one yet, so let's go ahead and we'll do this one real quick. All right, so they give us a right triangle here, and they're saying find the tangent of 2 theta. So I went ahead and I put the double angle formulas here. So we'll put the tangent of 2 theta. Now remember, this u, the angle could be u, theta, alpha, beta, gamma, all the different angles they put. So these can be easily substituted, x in some cases. So we'll say the tangent of 2 theta is 2 times the tangent of theta divided by 1 minus the tangent square of theta. All right, so the tangent of theta here, if you look at this triangle here, it would be opposite over adjacent, y over x. We're going to put 8 over 15 in there, so it would be 2 times 8 over 15 divided by 1 minus the tangent square would be 1 minus 8 over 15 quantity square. So then you just got to clean up this answer to get the number here. So let's see what I get. Right, I ended up with 240 over 161, so make sure you're careful on your calculations here, and let us go ahead and check that real quick. All right, we're in good shape there. All right, moving along, let's just continue here. Now, this is a good problem. Be careful when you're making this triangle here in the second quadrant. Again, the cosine number when you do the Pythagorean theorem is going to be negative. So I will let you practice on one like that. We did an example earlier. This one's similar in quadrant 3. Now, on this one, I would say if the cotangent of theta is 8, the tangent is 1 over 8. So draw your triangle in the third quadrant and be careful because y and x will be negative in the third quadrant. All right, and your r value or your hypotenuse will be positive. So that's a good little practice problem there. All right, now one other thing we wanted to look at here, not only we've talked about this in the past when we've done these formulas, can you go from left to right? You can also go from right to left. So notice here it says write the following expression as the sine, cosine, or tangent of a double angle, and they give you, it looks like the right side here, it looks like they're putting in 112.5 in for u. So if you go from this side to this side, you're actually doubling the u value. So if you take 112.5 times 2, I believe you're going to get, for this double angle formula here, the sine of 225. Now I'm just doing that in my head here. So, okay, I got lucky. So be careful. You can do that. Oh, and then they want you to do the exact unit circle value there. Now that would be y in the third quadrant. So once again, you kind of have to know your unit circle. It's just something that follows you here throughout the course. I've been trying to emphasize that to my students. You've got to know that unit circle value and so forth. So they're going to be all over you on this one. Now, also, this one's going to be similar. They're giving you the right side. If you double u here, the 135, I'll let you practice those. Oh, they threw pi over 12 in there. So this one would be the middle formula here. You double u, and that would be double pi over 12 would be pi over 6 here. So I would say 2 times the cosine of pi over 12 minus 1, so pi over 12 in here would equal the cosine of, I'll go ahead and do this one, I just like to have fun too, pi over 6, okay, and then that would be on the unit circle. I like to get these right too and have fun, the square root of 3, and it keeps your skill sharp too, over 2. Would be the pi over 6 value. All right, so let me go through. So the tangent one would be similar. Now, here's a verification problem with double identities. I always like to do these in the software and do them by hand to show you how it works. So let me go ahead here and set this one up real quick. All right, so on this one, if you're trying to verify the sine square x plus the cosine of the double angle equals cosine square x, on these double angle formulas in the past, it really hasn't mattered which one we've done to solve and get certain answers, but on a verification problem, I think it's going to matter big time. All right, so again, if you're verifying something, you've got to get everything here in terms of cosine square, so right away, you're going to use your Pythagorean identity on sine square, and hopefully you would just do this automatically because you know everything's got to end up cosine on this side. The cosine of the double angle then, which one of these formulas would you use? Well, actually, if you would have used this first one, now that I look at it, check this out. If I would have just left that sine square x there and used this first formula and I just put that in, I could say that's plus the cosine of the cosine square x minus the sine square x, and the sine squares will go out, and then you got it fried, dyed, and verified. But what if I would have gone this route? I mean, it's interesting to see how the software will go here. So this is one possible way to do it. Let's see if I would have stayed over here. Then I might have taken the cosine of the double angle and put plus the second one there to try to keep everything in terms of cosine. So sometimes when you're doing these verifications, you know, it just, when you're using the software, it's interesting to see how the software will present it versus how we just did it here. So watch what happens here. If you add these two together, you're going to get the ones will go out, 1 minus 1, 0, 2 cosine square minus cosine square. So there's lots of different ways to verify. And this is like, I like you to show this on the test. So, in case that, depending on how it approaches it over here. Now let's go ahead and pause and see what it does over here real quick. All right, so it says to transform the left side to the right side. And I kind of have to look at the pull down menu here. I'm going to think that they did that first option I did when I saw the first option. I'm going to say they probably should have said the cosine of 2x here. So there's more than one way to do these. I just wanted to work some of these out and show you. Should be changed to cosine square x minus sine square f, and the left side simplified. And that's really all they wanted on that one. So they didn't like do the verification like we would do, like super tough and stuff here. All right, now let me take one more of these power reducing formulas and I'll work it and then I'll sign off. I think that y'all will be able to go from there on these. So we've done some more double angle. We've got the power reducing formula here. So let me give you one more example on this one. 24 sine square x times cosine square x. Okay. All right, now on the power reducing formulas, I went ahead and I gave myself a lot more room on this one. You're going to have to get all trigonometric functions as an exponent of 1 here. So we're going to go ahead and use both of these. So I'm going to say in the next step, the sine square x, we're going to use the first one here is going to be 1 minus cosine 2x over 2. And the cosine of 2x here is going to be 1 plus the cosine 2x over 2. All right. Now remember, these 2 times 2's can come out. That would be 4 in the denominator. So this would almost be like taking this 2 times 2 and writing it out front here, which will make our life easier. It'll be 6 times 1 minus the cosine of 2x times 1 plus the cosine of 2x. Okay, so this will be 6 times, when you FOIL this, these are conjugates, you'll get 1 minus the cosine square of 2x. Again, when you multiply cosine times cosine, you'll get cosine square of the angle. Now don't mess with the angles again when you're doing this in this whole chapter. Be careful. When you multiply cosine times cosine, the cosine gets squared, the angle is not affected. And actually on FOIL, the O and the I went out on this, so that's why I kind of did this and to save some time on the video. All right, now once again, you don't have everything in terms of the first power, so we're going to have to use this one again. So we'll just come right under here and say the cosine square of 2x, just taking this and then doubling it, will equal 1 plus the cosine of 4x over 2. So that is what we're going to do in the next step. We're going to say 6 times 1 minus, and this is going to be, and here's where people get in trouble with these, 1 plus cosine 4x over 2. They don't show their steps, then they don't get a common denominator here when they substitute. They don't pay attention to the sign. Oh, bad things can just happen in there when you do this. So then multiply by 2 over 2. So then we'll get, I'll bring this over here, 6 times in the numerator 2 minus 1 minus the cosine of 4x all over 2. So this 1 over 1 became 2 over 2 here. And then I just went ahead and put that in the rest of it in the top. Watch the signs here. Notice this minus, oh, those signs in there. So this will equal 6 times, I tell you what, well, I'll just go ahead and simplify. 1 minus the cosine of 4x over 2, and then 2 goes into 6, so you can write 3 times 1 minus the cosine of 4x, or distributing 3 minus 3 cosine 4x. Now I'm going to go back to the software and see which one it likes, if not both. All right, now I'm back here and I'm going to go ahead and plug this in. I think I'm going to plug the first answer in here. 3 times 1 minus the cosine of 4x, not distributing it, just to see what happens. Now, believe it or not, sometimes it'll take that, sometimes it won't. Oh, it doesn't like it. So hopefully when we distribute it, it will like it. So let me go back here. I hope I didn't make any mistakes on that before. So 3 minus 3 cosine 4x. Okay, so apparently it does want you to distribute in the end, but let's say that you had did that on a test and you just forgot that last step. See, I would have gone back and given you lots more credit and stuff. All right, now here, this is getting back to the half angle formula. So you would take this and double it. We did an example with the angles earlier, so I'll let you do these. Okay, now let's do this one for the last example, and I will sign off here. Okay, for the last example on half angle formulas, it says use the adjacent figure here to find the exact value of the half angle, the sine of theta over 2. Now, looks like this would be a first quadrant angle here, although the triangles turn catty-cornered here. If we flipped it around, all these values are positive. So I'm going to come over here on the half angle formulas, and I'm going to put the sine of theta over 2 will equal the square root of 1 minus the cosine of theta over 2. All right, so let's just go ahead here and figure this out. This would be the square root of 1 minus, in this right triangle, cosine of this angle is going to be adjacent over hypotenuse, so that would be 24. So they might give you values to plug in for the angle here, and then you'll have to simplify. So this would be 1 minus 24 over 25ths, and the top would be 1 over 25 divided by 2. So that would equal the square root of 1 over 50. Now notice they want you to rationalize the denominator here too. So the square root of 50, if you simplify the radical, this would be 1 over, this would be the square root of 25 times the square root of 2. So you would get 5 times the square root of 2. So rationalizing the denominator, we will get the square root of 2 over 10. Remember, any square root times itself will become that number. The square root of 2 times the square root of 2 is the square root of 4, so this would end up 5 times 2. So be careful here. So we'll put in the square root of 2 over 10. All right, so now what you need to do is you must go and practice these formulas, ladies and gentlemen. You must get these formulas down, double angle, power reducing, half angle, in this chapter here that helps prepare you for calculus and how to simplify lots of things when you get there. The sum and difference formulas, very important. So keep practicing hard on these formulas. Get good at them no matter how they present them, no matter how they try to twist them and so forth. Remember that these led to all of these here with the Pythagorean identities. So go ahead and have at it. Bob Young signing off. Bye.